I'm very happy to introduce our next speaker, Arjun Singh, and he will tell us of connectomic analysis of an age-related neurodegeneration in random matrix denoised brain networks and revealed subnetworks. Please.
Thank you for the introduction. Sorry for the lengthy title. So today I'll be giving a little bit of information about the research I do in the field of connectomics, which is the branch of neuroscience that deals with the brain as a network, analyzing its topological properties in order to help understand phenomenon of brain connectivity patterns and understanding change as well. The previous presentation was actually a good theoretical introduction to some of the stuff we'll be talking about, so I want to thank him, but it looks like he's not here. I tried to leave some time for questions, but you can feel free to raise your hand in the middle or wait to the end. I'll leave that to you. So a little bit of background. Within the brain, analyzing connectivity is essential if we're trying to understand the specific mechanisms within it and understand how brain changes over time or as a result of external factors. So in connectomics, we model the brain as a complex network. This gives us insight and allows us to quantify the properties of the brain. And then we can look at these properties between different types of brain to identify statistically significant differences between these types of brains. Some examples would be those brains that are cognitively normal versus those afflicted with Alzheimer's disease, or older brains versus younger brains, brains under the influence of some medication versus a control. But this type of analysis has some certain methodological challenges. Obviously, the brain is very complex, so the data we're working with is very high dimensional, and we typically only have a limited number of data points we're working with if we're looking at a time series. And because of this, when we're trying to estimate connectivity within the brain, these estimates can be unreliable. Even compounding on this, trying to scan the brain, there are physiological noises and artifacts that are present just by turning the head, or a million little causes that can cause your estimates to become skewed or inaccurate. And traditional approaches to resolving these issues, such as a thresholding of the brain data, typically and can potentially discard valuable information that is essential in understanding the brain's connection. So, in my research, I seek to help address this problem by utilizing methods from the field of random matrix theory in order to identify true patterns of connectivity within the brain. Once I've identified these patterns, I then try to look for biomarkers between older and younger brains using the internal UF data set. So going a little more into the methods of how we actually do this, obviously the brain is made of neurons which have connections between them, and it would be great if we could model these networks and represent them, but unfortunately there's billions of neurons and how many more connections within that, so we have to do some simplification. So the first thing we do is we start with imaging data, and within that we then process the brain and project it onto an atlas, so we simplify the network into some X number of nodes, either based on functional relevance or anatomical location. In our analysis, our brains are processed into 300 regions of interest. Once you've done this processing, you then go back and look at the fMRI time series, and you observe how different regions co-activate, and you can estimate connectivity from that. And then you can process these observations into a correlation matrix, which essentially is just a matrix representation of how the different regions of the brain interact. So if you see we have some diagonals present. The main diagonal you can see is very bright because that's the self-correlation, the correlation of activation within itself. The way that our brains are parcellated though, the first 150 nodes are for the left hemisphere and the second are from the right hemisphere. So that's why you'll see diagonals kind of present here too. These are within the same network but on different hemispheres of the brain. Right. So after you've processed your brains and acquired these correlation matrices, then you can quantify topological properties through the use of these quantifiers. There are both nodal and global quantifiers. Nodal quantifiers essentially are typically measures of centrality or how important a specific node is within the brain network. Global quantifiers capture information about the brain as a whole. Things like how integrated or connected the brain is, or how the tendency to form modules with measures of segregation, and also resilience, like how does the brain hold up when we disconnect components. So this all seems great. And then once we have these quantifiers, we can then look at them between groups, for example, in young brains versus old brains, and then we can identify, well, difference in these quantifiers is an indicator of this specific change. And for old versus young, maybe it's not so useful, but for something like Alzheimer's disease, maybe this can be used to identify risk, and so you can start early treatment before the disease progresses. So this is all great, but as we said before, measuring and doing this processing introduces a lot of noise and a lot of issues. Even just looking at the correlation matrix, you can see it's almost, there's a lot of them are very light connections, but there's still connections, so it's a fully connected matrix. But it is known that the brain is not a fully connected network. So the question is, how do we deal with these sources of noise? We know that some amount of these connections are spurious, some amount of them are not important, some of them are the result of noise, so how do we deal with this? Well, to help address this, I utilize a method from the field of random matrix theory. So random matrix theory, as the name suggests, is the mathematical field related to random matrices, or matrices whose elements are derived from some probability distribution. In particular, with regards to correlation matrices, the Marchenko-Pastur law says that for a random matrix whose entries are IID and drawn from a Gaussian, all of the eigenvalues of these matrices will be fit within these upper and lower bounds, as you can see here. And any eigenvalues that fall outside these limits can be considered to be of significance, cannot be attributed to random noise. So you can see the diagram here, you can see the distribution fitted to the real data. So everything below this upper bound can be considered to be noise, whereas things that fall past that, we cannot consider them to be just the result of noise. There's some significance to them. So after we've identified eigenvalues of significance, firstly, we perform the eigenvalue decomposition of these matrices, and then using the upper bound that we've derived from random matrix theory, we identify the eigenvalues of significance. And there are a couple things we can do with them. The first thing we can do is use them in a denoising method. Essentially, after we've done the decomposition, we do something with the noisy matrix, with the noisy eigenvalues, and then reconstruct the matrix, hopefully in a manner that retains more signal and is more useful and more revelatory in our analysis. So when the method was first introduced in 1999, what they did with the noisy eigenvalues was to simply set them all to be the mean of them, but in later analysis they completely removed their contribution altogether. So you reconstruct the matrices using just the significant eigenvalues. The other thing that we can do is actually look into the structure of the eigenvectors associated with these significant eigenvalues themselves, and from them try to find patterns of connection within the brain, or in particular, a subsection of the brain that is of significance. So you identify the significant eigenvalues, but in order to extract some subnetwork or pattern of connectivity, we use the inverse participation ratio, which is a metric from localization theory, which essentially just quantifies how localized a system's eigenstates are. The inverse of this value gives us the participation number, or the number of components, which effectively is the number of components belonging to this subnetwork of significance. So, as I mentioned before, in my analysis, I looked at 86 brains from the UF data set, 24 of which were young, 62 of which were old. And I applied this, firstly I applied the denoising matrix on each of the brains individually, but what's shown here is the average results across them. You can see here this matrix is very light, so a lot of the changes were very subtle, but some were more significant than others, and here you can see where significant changes were. We can notice here along the diagonal, we see a lot of decreased correlation, which is promising because it suggests that spatial cross-correlations may be removed in the filtering process. And in addition, we see a lot of increase in correlation across different networks, which shows how different subnetworks are potentially more correlated than our initial estimates may have given us. So after this denoising process was applied to each of the brains, we then do quantifier calculation on the two groups and then compare them to identify statistically significant differences. And here's a list of some of the quantifiers in which there was a significant difference to be found. The ones of importance are mostly clustering coefficient and global and local efficiency. So essentially what this tells us is that younger networks tend to be more clustered than older networks. They form more specialized communities. And in addition, the flow of information is much better in younger brain networks than in older ones. So the next thing we do in order to identify the patterns of connectivity through the subnetworks is we first have to create a representative matrix of our data set. So essentially, we average all the brains we have together and then apply our Marchenko-Pastor distribution to identify upper bounds and find what eigenvalues are significant. So if you can see here, this red line here indicates the bound of noise. So any eigenvalue in the distribution that is less than this value can be considered noise, and anything above that would be signal. And we identified 9 different eigenvalues in our representative matrix that are of significance. And you can see here, we have one eigenvalue here that is quite a bit, like an order of magnitude larger than the other ones. There are those that are significant, but they fall closer to the distribution. But there is still one eigenvalue that is much larger, and this will be of importance later. So with these 9 eigenvalues, we look at their associated eigenvectors in order to identify subnetworks of connection. So for each eigenvalue, there is a pattern of connectivity there that cannot be attributed to noise. We can say that there is a significant result there. So here are just some diagrams of what these subnetworks look like. So the smallest of which only had 92 components of our original 300, and the largest of which had 269, almost the entire set of regions of interest. What's interesting here is that, or maybe not so interesting, it might be expected, that network 1, which has the most number of components, is the network that's associated with the largest eigenvector. So this represents like a global pattern of change or connectivity, which is what one would expect from the largest eigenvalue. After we determine these subnetworks, we then project out the submatrices for that specific network and then do the same quantifier calculations on those as well. And after doing this, we found that different subnetworks actually showed significant differences in different quantifiers. So some subnetworks only showed differences in the efficiency of it, but others show differences in the clustering or in the centrality of certain nodes. What's of interest is that in every single one of these 9 networks, efficiency was found to be significantly different. So just to wrap up some of the key findings from this, firstly, measures of network efficiency are the most reliable when it comes to determining differences between older and young brains. And our analysis suggests that maybe this might apply to other forms of analysis too, such as for other forms of neurodegeneration. As I said before, in all subnetworks, local efficiency was found to be significant. Another result was that distance-based metrics, such as the characteristic path length, the network radius or diameter, these are inconsistent throughout the denoising process. They were found to be significant in some networks and not in others, and in the original denoising method, there was not consistency in that. So that suggests that these might not be the best metrics to use for comparison between 2 groups. Again, we found 9 patterns of connectivity. What's interesting is that these patterns are not directly correspondent to known resting state networks within the brain. These appear to be, like, in a sense, novel patterns of connectivity. So further analysis is needed. All in all, RMT offers a promising new perspective to improve future connectomic analysis. I'd like to thank my thesis advisor who's not here, Dr. Bubenik, and my PI, Dr. Nino, and I'd like to thank you all for being here and listening to me. Do I have any time?
We've got time for questions.
Okay, perfect. If anyone has any questions, yes.
So there was a slide earlier on where you had this, you truncate, you get these large eigenvalues, you look at the eigenvectors, and there was some point, I just went past it, where you had the L4 norm of this.
Sorry.
One slide, I think after this, maybe? Yes, here.
Mm-hmm.
So this middle term, this L4 norm of these eigenvectors, can you give some intuition for using L4?
So essentially, if we have an eigenvector where, like, the relative measure of strength in each component, because we do the decomposition and we get 300 eigenvalues and 300 eigenvectors, the size of which is 300. So if we were to just look at that, we look at the significant eigenvalues, well, every component plays a role in the eigenvector to some degree. So how do we choose which nodes to actually include in that subnetwork? And to do that, we use just the top contributing ones. So for example, if we found the participation number to be 63, then we go back and look at the eigenvector, which are the 63 components with the highest relative measure, and whichever regions of interest those correspond to, those are what we define to be the nodes belonging to that subnetwork. Is that answering your question?
Yes, okay, so if I take the eigenvectors, I could just normalize them to be sort of L2 norm 1, that doesn't distinguish any of them.
Yeah, exactly.
And so you're trying to figure out
Exactly.
the distribution among
So
the components,
essentially,
where the big components and where the
yes, so
small
those
components.
with smaller relative measure, well, small to the fourth power will become very, very small.
Okay, so the point is, if I just took literally, if I use the L infinity norm, this is literally just the largest component, which is maybe too lossy.
Yes.
L2 norm spreads it out too evenly, so 4 is halfway between 2 and infinity. So. No, 4 is halfway between 2 and infinity.
Oh, yeah, no, you're right, Mike, yeah, no problem.
Okay, 4 is halfway between 2 and infinity. Thank you, yes.
It's a very informative symposium. Yeah, I was wondering a similar thing, like how you were choosing your threshold for the significant eigenvalues, but I think you just answered that question.
Okay, perfect.
Does anybody else have any questions? Very good. Thank you.
Thank you.